Alright, so in this video, we're going to be matching graphs and situations or scenarios, and these are going to be functions. So let's get into it. So over here, we're going to be filling up these containers with water at a constant rate. So the amount of water we put in is called the volume, and then we're going to be checking that with the height, or how tall the water gets inside each container. So this one's the widest here. So as we fill it up, it's like if you put in like 5 ounces or whatever, it's barely going to go up very much because it's got more on the bottom there. So this one's actually going to fill the slowest as far as the height goes. So this container goes with this graph here. So we put in 5 ounces, it only goes up a little, and then another 5, another little bit, another 5, another little bit, just as an example there. Now this one, because it's skinnier, like when you put 5 ounces, it's going to fill more height up, 5 ounces here, 5 ounces here, 5 ounces here, and 5 ounces here, or however much water you're putting in. And then so that's going to go with this graph here. So B goes here. And then this one here, it's going to fill slowly at first. So 5 ounces, 5 ounces, 5 ounces. And then it's going to start filling faster as you get taller up on the container. So that's going to be this graph here. So this is basically what we're doing on the video, is we're just looking at like some sort of scenario and then matching it with a graph, or on some of them we'll be going backwards, starting with a graph and then going to the scenario after that. But before we get into that, we just want to look at connecting some phrases we might see with the ideas behind increasing, decreasing, or the word constant. So stays the same, doesn't change, that's going to be constant. Rises, goes up, that's going to go with increasing there. Drops, that's a decreasing type idea. Going down, slowing down is also a decreasing idea there. So we just want to make sure that we're looking at some key phrases and at least in our brains identifying or connecting them with stays the same as a constant, going down or decreasing, increasing, going up, ascending, descending would be other ones that we might use there. All right, so let's look at this scenario here. So each day, several leaves fall from a tree. One day, a gust of wind blows off many leaves. Eventually, there are no more leaves on the tree. And then we're going to choose which graph goes with this scenario up here. So let's kind of highlight the main phrases there. So we have each day, several leaves fall. Then we have a gust of wind blows off many. And then eventually, there's no more on the tree. So when we're looking at these graphs, we do want to remember that we are reading them from left to right to show the passing of time. And these graphs are talking about leaves on the tree, not leaves on the ground. So another little piece of important information there. So if we look at graph A, we can see that this first section here, the leaves on the tree are increasing. Well, that's not falling. So this would be kind of the opposite of what we're looking for there. So graph B, graph C, those are our remaining choices there. So we have a decreasing and a decreasing there. So next sentence. So a gust of wind blows off many leaves. So on graph C here, the reason why this one is wrong is because this part right here is showing that the amount of leaves on the tree are remaining constant. In other words, no leaves are falling. Whereas on graph B, this section here, they're falling faster. So it's going down steeper or down faster than before. So there's our gust of wind right there. And then eventually no more leaves on the tree. So eventually the amount of leaves goes down to 0. So graph B is going to be the correct graph that matches this scenario up here. So here another scenario, we have air temperature increase steadily for several hours, then remain constant. At the end of the day, the temperature increased slightly before dropping sharply. And then again, choose the graph. So again, we'll go ahead and highlight the important phrases here. Increase steadily, then remain constant, and then towards the end, it increased slightly and then dropped sharply. So here we go. So on this one here, the temperature is staying the same, and then it increases, then it decreases, and then remains constant again. So on this one here, stays the same, increases, stays the same or constant, and then decreases or drops sharply. So this graph C, this one's the correct one. So here we go. So increase steadily. So increase steadily is here, and then remain constant. So remain constant. And then at the end of the day, increase slightly. So end of the day, increase slightly, and then drop sharply. So increase sharply, and increase slightly, and then drop sharply right there. So that's why graph C matches this scenario here. So real quick, we'll take a quick break from the graphs just to talk about another idea here, continuous graphs versus discrete graphs. So continuous graphs, you can have, like if you're talking about measurement, you can have like half an inch, quarter of an inch, you can have any number of inches. So that's continuous graphs. Or time, you can have half a minute, quarter minute, that type of stuff. Whereas discrete graphs, there's a separation between the first number and the second number. They can't continue in between. So most of the time when we're talking about discrete graphs, so those are things that cannot be split up. So like, for example, if you're counting number of people, so you can't have 1.5 people. Now I know sometimes like in math, we'll go ahead and average things out, like, so like the average number of people that, was 1.5, or, the average family has 1.5 kids or 2.5 kids or whatever it might be. So I mean, sometimes we see that, but if you're actually just counting the people, you're counting whole number of people. So that's what it would look like here. So you'd actually have a separation between one piece of information to the next one. You can't really so in math, though, basically what we do is to figure this out is we would draw like a line through this just to kind of show the trend, but the type of graph that we would use with counting people would be discrete. So here's some examples of things that would give us discrete graphs versus continuous graphs. So like a digital clock of this style here, it doesn't have the seconds or half a seconds or anything like that. So it's either 1024 or it's 1025. It doesn't show the in between. Whereas this one here, the analog one, we got that second hand that kind of sweeps around. That could be considered a continuous type information there, because we can have half a minute, quarter minutes, all that type of stuff. So another example here, trumpet versus trombone. So trumpet, you got your 3 buttons here, and I'm not a music player, so I'm just kind of going off of what I know, versus this trombone. It's got this sliding thing here, so you can get the notes that are in between notes, whereas this one here, you're only pressing the buttons there. So this would be a continuous, and then this would be discrete because you got the buttons there. Another example here, if we're talking about yardage in football, you can have half a yard, a quarter yard. You can talk inches if you want. Some people jokingly say, well, I guess they are kind of serious that football is a game of inches, even though, it's got yards there. Versus like your scoreboard, you're going to have whole numbers for your scores. So versus, home versus guest scores, even the downs and the yards to go, and all that type of stuff. So anyhow, that's kind of the difference between discrete and continuous. Another example here, if we're talking about coins, like if you got your coin jar, you can count like the number of quarters and the number of pennies and dimes and all that stuff, versus like if you put it on a scale, you could have 1 pound or 1.5 pound or 1.25 pound or 1.3296 pounds. So if you're like putting it on a scale, that would be considered continuous information, whereas if you're counting number of coins, you're going to have 1 coin or 2 coins or 3 coins and not in between. All right, so now we're going to go to sketching graphs. So here's a scenario here. A truck driver enters a street, drives at a constant speed, then stops at an intersection, and then continues. So here we go. What's happening? So we got to look at our axis there. So we're going to do speed on the y-axis and then time on the x-axis. We also have horizontal or vertical axis there. So basically what's happening here is it starts out by increases. So enters a street, so the speed is increasing. Drives at a constant rate, remains constant, and then stops at an intersection. Well, we have to decrease to a stop and then continue. So it's going to increase after the stop. And then he or she is going to go back to doing the speed limit again. So here we go. So initially increases. So that's going to be an increasing graph from left to right. It's going up. Then it's going to remain a constant. So we're cruising at 25 or 35 miles an hour. And then we're coming up to a stop sign. So now we're going to have to slow down. So that speed's going to have to go down to 0. 0 when you stop. So probably looking both ways. And then we're going to get going again. So that graph is going to increase. So we got to go back up to the speed limit and then remains constant after there. So this is a speed versus time graph. Now, if we actually had like numbers and stuff, we could put that, for 25 miles an hour, 35 or whatever it is. And then if we actually have the time there, we could have specific times that we're working on, for an hour or 3 minutes or whatever it might be. So here's differences between your axis. So here's a scenario here. Both graphs show a relationship at a child going down a slide. So graph A here, it's distance from the ground, and graph B here, it's speed, or how fast the child is going down the slide. So distance from the ground, or altitude, or height, you could also put that there. So it starts at the top, goes down the slide, goes to that little slowdown area there, and then hits the ground there. Well, so that's a distance from the ground. Well, let's look at the speed. So he starts out going really slow, and then when he's like halfway down the slide, his speed is at its, he's going the fastest there, and then he's going to slow down as he hits this part right in here all the way to a stop. So even though this is the exact same scenario, graph A, graph B, they're looking at different aspects of the scenario. So we do have to make sure that we're paying attention to what is it that we're actually measuring, because the graph can look totally different if we're measuring height versus how fast something is going. So now we're going to sketch a graph for this situation here. So Henry begins to drain a tank of water by opening a valve. Then he opens another valve. Then he closes the first valve. He leaves the second valve open until the tank is empty. So what's happening here? So as time's going, we're going to put that on the x-axis or horizontal axis, right? Moving left to right, we're going to have time. And then water level will be on the y-axis, or it's also called the vertical axis there. So basically what's going to happen is when he has one valve open, it's going to decline. And then when he opens both valves, it's going to decline more rapidly. And then when he closes the first valve, it's going to decline, but that decline is going to slow down because he doesn't have both of the valves open. So here we go. So declines slowly with the one valve, and then with the both valves declines faster, and then with just the other valve open is going to decline slowly again until it drains. So the length of these might change depending on how you're reading this, but this is the basic shape that your graph should look like there. So now we're going to go backwards. So here we're going to start with the graph, and then we're going to be writing a situation for that graph. So we have speed versus time. So as we go from left to right, the time is increasing, and we can see what the speed is doing here. So basically what's going on here, again, x-axis is going to be time, and the y-axis, that's going to be speed. So we're looking at the comparison or the correlation or the relationship or something like that of speed versus time. And so now we got to look at the sections. So basically it's going to start by decreasing. So that's this section right here. Then it's going to remains constant, and then it's going to decrease down to 0. So now we're ready to write our scenario. So, I mean, if you're thinking like you're driving around, you can start looking at this spot right here, right? We start on the left and work our way to the right. So we're going to start here. So this person is slowing down. So let's say you're driving along and the speed limit is 45, and then you come up and now it says, oh, you're coming into town. So now you got to slow down to 25. So a car approaches traffic, slows down, then drives at a constant speed, and then slows down till coming to a complete stop. So this here, the speed limit's like 45, and now he's got to slow down to get to 25, so he stays at 25. Then he comes to a stop sign or a stoplight or gets home or whatever, and then he slows down to a stop as he gets into his driveway or comes up to the stop sign. So this is a possible scenario you can write for this graph here. All right, same thing here. Go ahead and take a minute and try and come up with your own situation for this graph here. And pause the video, come on back, see how you did. So here we go. So we do have to pay attention to the label here. Water in the bucket. We're looking at height versus time, or that correlation there. So a possible situation for this is the water level stays the same, so you got just a bucket sitting outside, and then it starts to rain. So, and it rains pretty hard, so it's that bucket is going to fill up with water there, and then the rain slows down a little bit. So how fast it fills up is going to slow down also. And then somebody dumps out the bucket, and this could be, it looks like it's going out pretty slowly. Maybe a better one for that would be, it's got a leak in it. So anyhow, you can think of it kind of that way, or it developed a leak, and then the water leaked out from there. So as far as the variables go, your x variable, that's going to be time, and then the y variable, that's going to be height there. So, and some people, again, will call this the horizontal axis is the x-axis, goes with time. The y-axis is vertical, goes with height. All right, so in this graph here, we can look at what's going on here. So we can see here it's labeled air in the balloon, and we're looking at volume versus time. So what are the variables? Well, the variables, we're going to have volume and time are the variables, and then describe what's going on this graph here. So here we're looking at volume in the balloon. So it's getting bigger, then it takes a break from getting bigger, stays constant, then it gets bigger again, takes a break. So basically what's going on with this is that when you blow up the balloon, that's what's happening here. When you're getting more air in the balloon, you're blowing it up, and then you take a breath here when it flattens out because nothing's happening to the balloon when you breathe, and then finally at the very end, it's going to pop. And so the volume is going to decrease down to 0, and it's going to happen really, really fast. So that's why we got this sharp decline there. So go ahead and take a minute, pause the video, write a quick possible situation for this graph here. So here we have college savings versus number of months. So that's going to be our variables. It's going to be months versus money. And so our situation that we could do is we look at it, well, it stays constant and then drops, and then stays constant, then drops, stays constant, then drops. So, and then it keeps repeating that. So basically what's happening here is that each term, this is the college savings, so it worked all summer or whatever, and so we've got this much in our college savings, and then when the term starts, well, now we got to pay tuition, so it drops immediately. There's like not even a line there, it just skips straight down, so it goes, start at 25,000 and then drops 5,000 or 10,000 or whatever it might be, depending on what school you're going to, and then drops suddenly down to the next one, and then pay tuition again, stays that way for the rest of that term, a month or two, or well, be a couple of months, 3-4 months, whatever it might be, and then drops again suddenly, and then a few months go by, next term drops suddenly. So that's basically what's going on with this graph here. So just remember with these graphs, we do want to pay attention to what our variables are. In this case, it's speed and time, and we're looking at the airplane here. So for this one here, remember we want to use the keywords in the description. This one, there's no description, but we can look at our variables there. And so, he's taken off, and so his speed increases, and then now we're at the flying altitude speed, and then slows down and comes to a stop when they land. So, but now if we were to switch up our variables here and look at altitude versus time, well, this one's going to stay the same. Whereas this one here, his altitude or her altitude goes up, and then, oh, we got turbulence out here, so we're going to drop down to a different altitude and fly lower, and then come down for a landing there. So although this graph stayed exactly the same, this one, if we're looking at altitude, could change. I mean, this person could be going crazy as well, going like this. And so it's all, going up and down and up and down. But the speed is staying the same, but that altitude is changing. So your two graphs could be vastly different depending on what variables you're looking at. So just keeping that in mind, remember when we're looking at these graphs, we're looking at the keywords and then increasing, decreasing here, staying constant, and just keeping those in mind as we analyze these sections of graph.